Hello, welcome back. Today we're going to be looking at getting our website to not have to be accessible by an IP address, for us to actually be able to give it a name. And unfortunately, I couldn't find a better free DNS service out there than free DNS. When I do this for my personal devices, I like DNS. It costs like $20 a year for like 10 addresses, or like $50 a year for significantly more. So if you have a lot of different devices around the home that you want to be able to access by name instead of having to remember their IP, it's pretty cool for that. It used to be very useful for things like security cameras and other devices that you want to access around the home to have that kind of DNS available for devices all over your network. Today, it's not that big a deal. But again, they're pretty affordable. There are a lot of cheap DNS services out there, but there's not a lot of good free ones. DNS doesn't have a free tier anymore. No IP is another popular one. That one doesn't have a free tier anymore. Free DNS still does, so you're going to look up free DNS. The website is afraid.org or freedns.afraid.org. There are a limited number of free subdomains that you can use, but once you've signed up and registered your email address and come back, you're going to end up on the subdomains page. At that point, all you have to do is add your subdomain. So you will pick a subdomain. I picked Crab Dance. There's also Chicken Killer, Ignore List, Jumping Crab, Moo, Strangle.net, Twilight Paradox, and many others. You can pick any of these subdomains or domain addresses. Then pick your subdomain. So whatever you want the name of your website to be, dot the subdomain, dot whatever their extension is. Most of these are com, but there are some that are net and stuff. And then on the destination IP address, you're going to set the destination of your workspace. So I did what's my IP in my workspace again, and made sure that I got the IP from there, and I made sure I put that in my subdomain. So this is not going to be it. That's going to be my IP here at home. You want to put your IP of the workspace. Okay, so with that completed, you will have your subdomain pointing to the address that you want it pointing to. Unfortunately, FreeDNS is really not performant at the free tier anyway. If you pay money for it, it's pretty good. So it could take like an hour for the DNS to actually propagate out, which is why I mention it now. Mine still hasn't propagated out, and I did this like, I don't know, 15 minutes ago, so it can take some time. So if you want to see an IP address being converted into a regular name, follow the steps here. And in the meantime, we're going to learn about DNS. But first, before we do that, let's look at what our PHP script traffic looks like in Wireshark. So remember, we set this up as PHP traffic, and I just want to show what that HTTP to PHP connection, all that different traffic looks like. So remember, we learned about all these different HTTP headers and stuff. If we try to make, this is a fetch from Eclipse to the server, and this is on the client's end, so this is looking at the fetch from the client's perspective. We see that it is an HTTP post. Well, let's look at some of these headers by examining the HTTP protocol details here. So first you see it's a post, PHP, fetch.php, you see the version, this is HTTP 1.1. We see -r-ns at the end of every line. Remember, headers are each on their own line. -r-n is the new line character on Windows. We see that our user agent here is actually Java, so we don't identify as a web browser. Normally you'll see something like Chrome or Firefox, like Gecko, whatever the different browsers call themselves. Here it does actually specify that it's Java, because that's the application that we send the message from. So for different web servers, it's usually relevant what browser you're communicating from. And then there's usually a category of other. You haven't used any of the browsers that we expect. Some badly configured websites will say, go download a browser that we support. Others will have a default page they send to the browsers they don't expect. Java 11 is probably one of those browsers that nobody expects. but that's okay. We support it on our web server because our web server doesn't really do much. We've got the host name there that we're targeting. We've got the kinds of information that we will accept. Yeah, Workspace takes a long time to start up if it's not already online, but we're not going to use it much today, so don't worry about it. You just want to get your IP address off there, so if you can't do it, it's not a big deal. We're going to accept text, HTML files, and then we're going to accept GIFs and JPEGs as image files. So we're accepting a few different kinds of files as responses. We're going to keep this connection alive. We've got some other junk here, all kinds of different headers. I'm not going to go through them all. Then we get to this other tab in Wireshark where you can see the payload of the HTTP message, so the HTML form URL encoded. This is the info that we sent. We sent for item user ID, we sent fish. For form item data 1, we sent the password. Form item data 2, we sent last login. So that's the user ID column. We're looking for fish for data 1, which is the column we want returned. We want the password column. Data 2, we want the last login column. You can expand that for more detail there and see that we supplied both the key and the value. Both the word data1 and password were supplied by us. If we look at the response, we see that, again, in that second tab, we see the response connection established, fish, which was the user that we were looking for, and then the word data, and then another new line, and then their password. The PHP scripts use -n manually instead of -r-n as their new line character because, I don't know, that's just the way I wrote them, but it should be -r-n because we're all pretty much on Windows platforms. -n is the new line character on Unix platforms. And in that response, we see another bunch of headers as well. We see that this header tells us that the server is running a Microsoft IIS 10, so you can tell what kind of server you're getting a response from. So if you want to go look at your Wireshark traffic from just a little bit of internet browsing, sort all of your HTTP messages and see what kind of servers you talk to, you'll find very few IIS servers. You'll mostly find, again, Apache and other Unix-based servers out there for the most part. You'll probably also find that most of them now are hosted on Amazon's cloud or a similar service somewhere. So you might see some with some kind of indication that they're a VM in their name. You see powered by, which gives you the version of PHP and ASP.NET that we're using to power the server. So also information that the client gets back. It indicates that the content type here is text. We get the date, we get the content length. You can see that, again, another length field. There was a length field in TCP, there's a length field all the way down, right? So we get yet another length field here. Time since the last request, and then the full URI, and that's about it. So a couple things to note here. First of all, the information sent over HTTP is sent unencrypted. This means that anybody in between us and the destination can snoop it, so this is not ideal for sending private information like passwords. If you're going to send information like passwords in the clear like this with no encryption, you need to make sure that you've thoroughly encrypted the information and that it can't be decrypted in transit. That's not good practices at all because it's very hard to implement, so generally you're going to want to get HTTPS working. Now the first step generally to get HTTPS working is to get a DNS name. Getting HTTPS on an IP address is not common because IP addresses, number one, tend to change unless you pay extra for a static IP. And number two, it's just a little bit more difficult to verify that you're the owner of an IP address. It's a more convoluted process. You need to basically put a file on your web server. The certificate issuer goes and looks for that file. If it finds it, then it confirms you. It's a little bit more of a process where it's for DNS-based authentication that you're the legitimate owner of a domain. You just type a couple of commands on the machine that you're trying to authenticate, and it's all done. It's very simple. So don't send important data over HTTP. Try to get this to HTTPS if you're using it for something important, a real application. You would try to get this to communicate over HTTPS instead. If you're just sending not serious data, or if you're sending stuff that's I don't know, already thoroughly encrypted and you're sure, then it's fine. An example of this might be just like archiving data for yourself or something. It's probably not high risk, so you can do this by all means. Okay, let's see if I got my DNS record yet. Nope. Okay. It also might take a while for my browser to decide to check that website again. I might have to clear my DNS records before it does so. In the meantime, let's look at DNS and how it works very briefly. So, if you'll remember back from the link layer, ARP translated MAC addresses to IP addresses, and that was useful for communication. DNS does an even more important step, which is translating regular English names to IP addresses. So names like jager.crabdance.com to the IP address of my workspace. And, of course, google.com to whatever it might be, and catforums.com to wherever it might be. Those aren't the right IP address, by the way. Those are just random. But DNS is considered an application-level service, so it runs on top of, generally speaking, UDP. Let's have a look in more detail later. All around the world, there are DNS servers that you can talk to inquire who has a particular domain, who has the English name of a particular domain. When we're asking who has, that means what is the IP address for that domain. The majority of people in the world do not configure their DNS settings, and they use the ones provided to them by their internet service provider, by their ISP. So your ISP, obviously, as part of your internet service, has to make you able to use the internet. One of the services that they provide you is a DNS server. Their DNS server usually sucks. It's usually relatively slow. It usually goes down occasionally or is just lagging occasionally, so sometimes your internet will be a little bit slower because their DNS server is slow. And the worst part of the ISP DNS is typically that when you type in a domain that doesn't exist, DNS is supposed to respond with nix domain, which is what I get when I try to go to jager.crabdance. This is a good response. DNS probe finished, nix domain. Now, if you try to visit your domain that you've set up that hasn't been registered yet, so you don't get to it correctly, and you don't get this page, instead you get a page from your ISP. Many of you will, who are using your ISP default. So instead of getting a nix domain, you'll get a page from your ISP that says that page wasn't found. And oftentimes this page will contain ads, or in the worst case, they will actually redirect you to their ISP's search engine. So AT&T has been guilty of this in the past. If you type a domain that doesn't exist, they'll take you to the AT&T search engine page and show you that the page doesn't exist, which isn't what you want. You want it to just say this domain doesn't exist. But none of those are really a big deal for people. The ISP's DNS is usually perfectly fine. It does what it's supposed to do. But then there are a large number of other services out there that offer free DNS resolving. Not the DNS like registering your domain like we did just now, but free DNS resolving, and they run their own DNS servers. Google's the big one for this. The reasons that they do this for free are pretty various. We won't go into that in too much detail, but they offer high performance DNS servers for free. Google, Cloudflare, Level 3, there are many different options for you. Now there's a tool called DNS Benchmark, which you can download from the internet. Post a link if anybody's interested in Discord. And DNS Benchmark allows you to test from your home connection which DNS server in the world is the fastest for you, and then you can set your DNS servers to that one to improve your browsing experience. So you should run it at a couple different times of day when your network's not under too much load. See what the best DNS servers are for you in terms of response rate, and sometimes that can improve your internet browsing experience quite a bit. Registering a domain, so getting a DNS, typically costs money. That's what we just saw with the free DNS there. Now, there are services like free DNS that let you register a subdomain for free, but if you want your own top-level one, like if you want to register crabbattle.com, you're going to have to pay for that, and that money is going to go to ICANN, who basically administers the domain name servers for the entire world. So it administers the giving out of the English names relative to IP addresses for the whole world. DNS servers are frequently going to update their list with the official registry of who owns what. So there's basically a coordinated list of who owns which domain that the entire world has to coordinate somehow. Let's look at how they do that a bit. So it's basically the directory service of the internet. It's kind of like the phone book of the internet. You look for a name and it'll tell you where it's located in terms of IP address. If you consider how humans are numbered, we have all kinds of different numbers that correspond to us, our social security number, driver's license, etc. And then these typically translate into our common name. DNS is doing the same thing. It's translating our well, it's doing the opposite thing. It's translating the common name to the social security or driver's license, or in this case, IP address. Obviously, it's a core function of the internet because if we all had to memorize IP addresses, it would be a very bad time indeed to try to browse. A DNS server will listen on UDP port 53 typically. They will typically run a single application called Berkeley Internet Name Domain bind. This is a Linux-based application. Generally, it's open source. It's very old. It doesn't get updated particularly often. It does the job it's supposed to do. It's basically been in service for decades. There's other software out there, but it's significantly less common. There's a Windows-based as well for some places that prefer Windows-based. I think at JCU, if anybody knows, I think we have a Windows-based DNS server for our internal stuff like banner and everything. I think we do that, so I'm not sure. So let's look at what a sample DNS request might look like. So first of all, DNS is running over HTTP, so we're making an HTTP, no, sorry, it's not running over HTTP. When we contact a website, we're contacting it over HTTP. Backtrack. DNS runs over UDP and everything. When we contact a website, we contact them over HTTP. We're making a GET request for a particular URL, an English name. When you submit that GET request to your browser needs to be able to send it to the IP that it's going to, the address that it's actually destined for. So the browser extracts the host name from that GET request, and then it passes it along to the DNS portion of the application. You can set up your DNS at the browser level, at the operating system level, at the router level. We might go into that in more detail if we have time. But basically, your browser passes it along to the DNS portion of the application, and then the DNS client figures out who has catforums.com, and once it responds, then you can do your HTTP GET request as you are doing it, because until you get that response, you don't actually know where to send the GET request. That means that the entire DNS process has to finish before you can even begin to contact a website out on the open internet somewhere. That means that DNS is usually the slowest part of connecting to a new web page. So when you connect to a new page for the first time, like catforums.com, which probably none of you had visited, it takes a while for the DNS response to come back and tell you where it is located. That's usually the longest part of page loading when you're browsing on the internet. So okay, the DNS client asks the DNS server which IP address owns catforums.com. The DNS server responds with that IP address, passes it back to the browser, and then the client completes the GET request. Now, how do you pick a DNS server to use? All right, so if you want to pick one just for your computer to use, for Windows users, you can go to your IPv4 adapter properties, and there's a box that you can change there, which will override whatever network settings are on the router. So this will work. This will override all settings except the browsers, which can override this again. But anyway, if you want to use a particular DNS for your machine, you would do that. If you want to use a DNS for your entire network, you would sign into your router, and you would find the DNS server settings in your router, and then you can specify them there as well. Then all the devices on your network will use that particular DNS. Now, if you hardcode your DNS to a device the way that was done on the left there, so if you're hardcoding them for your device on Windows, that raises an interesting cybersecurity problem for certain devices, particularly things like smart TVs at this point. So one of the best uses for consumers for DNS is to block advertisements, and the way that's done is very simple. There's a list of the servers, the names of ad servers out there that you can access, and whenever your device on the network tries to access one of those, instead of returning the IP address for it, it just returns it nix domain or loopback, so that the ad can't properly load because your machine can't actually establish a connection to the ad server. It's a great way to block ads. The Pi-hole uses this approach. I have a Pi-hole on my network, and it blocks ads perfectly. It blocks ads before they even get to uBlock, which combined with uBlock allows you to have even faster and better ad blocking. But it also blocks ads on devices like your phone and your smart TV, where changing the DNS settings is a little bit more difficult, and installing an ad blocker can sometimes be a little bit more difficult. So what some device manufacturers have started to do is basically hard-code DNS addresses like 8.8.8.8 there, which is Google's DNS, into their device so that no matter what DNS settings your network tries to enforce, they will use that DNS server to communicate. This allows smart TVs to bypass the Pi-hole and send ads. So manufacturers like Samsung have already adopted this strategy. TCL did not, so TCL wins in that category despite being a Chinese TV. You'll often see these lower cost TVs actually end up being better for ad blocking for some reason than some of the ones that are something like $4,000. I feel bad for all of you who buy a Samsung TV. Why don't you comment in either chat how many ads you get on your smart TV if you have one? How bad is the smart TV experience? And if your smart TV experience does suck, get a Pi-hole and it might help. There are also ways to force DNS to redirect to your network's settings, but it requires some firewall magic to do so. And that requires a network level firewall, so a little bit more money there because those aren't free. Okay, so, but the reason that a lot of manufacturers do this, even though it's kind of nefarious, there's also a less nefarious reason to do this, and that's that the customer's DNS, remember, usually defaults to the ISP's. And again, the ISP's DNS is occasionally terrible. So when your smart TV or other smart device stops working and you call their customer service and the problem ends up being that the ISP's DNS wasn't responding correctly, that's a bad time for them. Whereas if they simply hard code Google's DNS to their device and always use it, Google's DNS is very reliable. That means less calls to customer service. So that's the non-nefarious reason to do this. So if you ever end up being an application developer for some kind of smart product, I can definitely see the argument for doing this both ways. But I'd like to ask you to please include a way to change the DNS settings on your device if you're going to do this. Unless it's like a smart light bulb or something, then I guess it doesn't matter because you can't get ads on a smart light bulb. Okay, aliasing. So many sites have multiple URLs that end up pointing to the same place. So Google owns most of the different combinations of Google with various numbers of O's in it. Then the top level host name that all the other ones point to, that one is referred to as the canonical host name. So obviously Google with 2 O's is the canonical one, we would assume. This is usually called the C name in IT, the canonical name. And then all the other Googles with different numbers of O's will just end up taking you there. But it is not necessarily the most mnemonic one. So sometimes you think that it's Google with 2 O's, it'll actually end up taking you somewhere else entirely. So many websites have a bunch of aliases, but they don't actually take you to the one that you might be most familiar with. This can happen if a company or a website used to be known under a different name, then maybe after a merger they acquired another company's website. Now they're more known under their new name, but it's actually still their old domain that, comes in. Yeah, I can see a light bulb trying to play an ad for me somehow. Maybe they'll install a speaker in them or something, or maybe it'll broadcast the light on the wall in a particular pattern. I think the future cybersecurity network dystopia that's most likely is that we're just going to have ads in everything. So DNS is used to map aliases to canonical names as well. And each alias might be on a separate machine. Obviously, Google.com is not on a single machine because it has to service the entire world. There are actually tons and tons of Google.coms all around the world, clones of one another. They probably communicate behind the scenes quite a lot. But when you connect to Google.com, you connect to one of its many aliases. So let's look at how email aliasing works. This is one of those examples where the mnemonic name is not the one that's actually the canonical name. So your email, which is like abcd@site.com, is actually more like abcd@relay.east.site.com. So there's a canonical name with more detail. That's a lot more complicated. DNS is also used to map this alias to the canonical host name. Some companies have a web server and an email server at the same host name, so they'll have the website and then they'll have the host name too. In this way, DNS can also be used for load distribution. So popular websites, again, like Google, are cached all around the country. If one copy of that website, one location of it perhaps, is overloaded, then DNS can direct traffic to a different copy. So this isn't really one of the designed uses of DNS, but it is one of the ways that it's used in practice. So large websites resolve to multiple aliases, multiple IP addresses, and a very simple form of load balancing, so making sure that you don't overwhelm one IP address while all the others have nobody connected, is that when you make the DNS responses, you rotate the order that those addresses appear in. So when you're responding to client A's request for what is the IP of catforums.com, you give them one IP address. When you respond to client B's request for the same thing, you give them a different IP address. Then client A connects to the one IP, client B connects to the other. They're both the same service. Whatever they do behind the scenes to synchronize is irrelevant here. But now we've connected to those two different machines, which might be in different physical places, and that guarantees that not all of the requests go to A. So you might issue a DNS request for the same website and find that you get a set of IP addresses in a different order when you issue that request again later. So you might get you'd probably get the same IP addresses, but you'd get them in a different order. So let's look at an example of how to do that with the load distribution. So client asks a DNS server who has catforums.com. The DNS server responds with the canonical name of it is catforums.com. Here are its aliases, catforumswest.com, catforumseast.com, and here are the IP addresses of the canonical and then its two aliases. All three IP addresses, both aliases, all of those lead to catforums.com. If we shuffle the order of the IP addresses, typically your browser will just try to connect to the one it sees first. If we shuffle the order, then different browsers will try to connect to different aliases, which helps us distribute the load of connections that we receive. Now let's look at the global DNS network, so how it works for the entire world, how it handles the workload of the entire internet. Someone logged in there. Free DNS and gave you a phishing warning. Let's see. Well, it's not exactly a... man, mine's still not up. Maybe I spelled it wrong. Yeah. It's not exactly a well-known domain name, and you might have, for all you know, had it with a different... that somebody else might have had the name earlier or something, so... it might look like a phishing attempt from that perspective. We're also not encrypting any of our traffic. We don't have HTTPS set up yet, so there's a lot of suspicious red flags from the browser's point of view when you visit a weird domain like that. So to handle the workload of the entire internet, DNS servers, like certificate authorities from earlier, are split into a big hierarchy with many parts. So first you have the root servers. The root servers are the top-level authority in the world, and there are not very many of them. But look at where they're at, okay? There's VeriSign, which is a US-based company. They own two of them. US universities, I think Berkeley and Stanford, maybe. So a West Coast and an East Coast. I might be wrong about exactly which two. Then there's NASA, the Department of Defense, and the US Army has three, so those are all American, so we've got quite a few American ones so far. ICANN and the Internet Systems Consortium are mostly American. Cogent is a US-based ISP. They've merged with somebody else, I think level 3 or something, so, but again, US-based. And then we finally get to NetNod and RIPE, which are EU-based, and then WIDE, which is Japan-based. So almost all of the root servers are in North America and in the US, more specifically. There are only a couple in the EU, and all of Asia gets one, and of course Africa, Australia, and South America have effectively none. Now these get copied into many different physical locations, and these root servers do not store the name and IP address of every website in the world. Instead, they store the addresses of the top-level domain servers. The top-level domain servers are responsible for an entire top-level domain like com, edu, us, gov, net, org, etc. .com is obviously by far the biggest domain. .com is supposed to stand for commercial, but many organizations that aren't commercial or for-profit entities still use .com. There's no restriction on that anymore. It was originally operated by the Department of Defense, but then it was basically privatized and sold to VeriSign after they purchased Network Solutions, and I think VeriSign has had it since. VeriSign makes a pretty considerable chunk of its money by administering that domain. And then remember also that VeriSign is one of the larger certificate authorities, so that's another one of their sources of revenue. Net and org are also owned by VeriSign now. Gov must be under some legal whatnot owned by the US government, so it is, but VeriSign basically administers it for them. So although the government is technically the owner, it's basically VeriSign's responsibility. Likewise for EDU, it's technically owned by EDUcase, but basically just administered through VeriSign. So VeriSign basically owns all of the most important top-level domain servers. Now the other national servers you might know of, like .uk, .ru, .tv, which is an island in the middle of the Pacific somewhere. All of those are national servers. They're usually owned by the government of their country, whatever that may be, and probably also contracted to VeriSign for administration. So the top-level domain servers, of which there are many more than there are root servers in the world, these are serviced by other organizations called registrars. Registrars get accredited by ICANN, which is, again, the organization that's basically in charge of the different protocols on the internet. They get accredited by ICANN as a licensed registrar, and then you can register a domain with the organization that owns the top-level domain. So when you register catforums.com, you're basically buying it or renting it from VeriSign, essentially. But there's that intermediary in your way, the registrar. So you buy it from the registrar, and then the registrar basically buys it from the TLD. And a little bit of money goes to ICANN for supporting their work as well, I believe. So when you register a DNS, when you register a name, your organization will provide the name of your authoritative DNS server to the top-level domain server. So the TLDs, instead of storing, again, your website directly, they will store your authoritative DNS server. This is owned by individual organizations, but more now it's owned by the different organizations that host web content. So most people don't do their own DNS anymore. They don't build their own authoritative DNS servers. They use a DNS service. FreeDNS probably uses one too, but then obviously if you host your website on Amazon or even GoDaddy or something like that, they're all going to have their own authoritative DNS server as well. Any organization that hosts public web content either needs to build their own authoritative DNS server or pay someone to manage it. Not a lot of free ones out there again, but there are some. You are going to probably pay, if it's a hot domain, you might pay $1 a month, but really it's cheap. DNS management is, this part of DNS management is cheap. It's usually this cost is usually dwarfed by the cost to register your domain and keep that registry up to date, especially domains with hard to find names, so good names, those can be quite expensive. So the authoritative DNS servers provide publicly accessible records that then map the host to the organization that owns the IP address. So now you're getting to the part where it actually maps to the IP address of the website itself. Really big companies like Google will have multiple authoritative servers. Most competent IT departments that need one will have at least one backup. You definitely don't want your authoritative server to be down or nobody can access your service. So a lot of enterprises will have their own DNS. think again JCU has one that allows access to the VPNs and internal services, like we have Banner, for example. So you have to have a DNS server to operate those. And then those will usually have at least one backup. And then we get to the local DNS server, which is the one that you actually get to change in your setting, the one we were referring to earlier, that you can change on your router or in your operating system. Again, these are generally provided by your ISP. Some organizations will run their own, and some users will opt to use public ones, like 8.8.8.8. So that's actually a local DNS server. Even though it's definitely not local in terms of location, it serves the entire world. It definitely takes a lot of requests, so it's weird to consider it as a local DNS server. It probably takes far more requests individually than any of the routes do, any of the 13 routes, but still it's considered local. And again, the fastest local server is often based on your location. You can't really say that one is faster than the other. 8.8.8 is usually really performant in North America. It's pretty good. Cloudflare's is pretty good in our area, 1.1.1.1. Level 3's is pretty good in our area. Those three are usually neck and neck in the Midwest where we're at. So let's look at how a DNS request might work if it has to go through the entire song and dance. So a client sends a request for gaia.cs.umass.edu, and it sends that to their local DNS server, which is at dns.poly.edu. So the local DNS server will ask the root, that's step one. The local DNS server will ask the root who has the top level domain for .edu, so who's in charge of administering edu. The root DNS, that's request 2, will respond with who is in charge of that TLD. Then we'll talk to that person, the TLD DNS server. We'll ask the TLD who is the authoritative server for umass.edu. So we're getting a little bit closer. We're getting to UMass, but still not to the website itself, just to that organization. So in the case of my FreeDNS, who has the authoritative server for Crab Dance? Probably FreeDNS does. Who has the authoritative service for Com? That would be VeriSign. Alright, so the TLD will respond with who has that authoritative service. If it doesn't know, which is occasionally the case, then it will pass along the address of an intermediary, another DNS server that will know. So there might be some more steps in here as you get redirected. Next, the local DNS is going to ask the authoritative server for the IP of the website you are actually looking for, gaia.cs.umass.edu. You'll get their IP address. It will pass that along to the client, and then the client will be able to connect to them. So a couple things to note here. First of all, that was a lot of steps, which means it's going to take quite a long time. Now this is UDP, so there is no handshaking involved, so at least we don't have that overhead. But the latency is quite long, right? We have to wait once between the client and the local DNS server. Then the local DNS server has to send something to the root, get something back, send something to the TLD, get something back, send something to the authoritative, get something back, and then finally send something back to the host. That takes quite a few steps. We're looking at 4 round trip times here with different round trip times since we're talking to different machines. Another thing to note here is that the local server does all the requesting on your behalf. So the client only tells them who it's looking for. The local DNS server does all the looking for you and then responds to you. So from the client point of view, all you see is a request and a response. You don't see all of these other steps. So if you want to look for all of that happening, you would have to have a local DNS server. If you wanted to see that in Wireshark or something, you would have to have a local DNS server to track. From the client point of view, all we see is we send a request and we get a response back. Let's look at what a recursive DNS request might look like instead. Oh no, I cut off the T. Okay, so the client sends a DNS request for gaia.cs.umass.edu to their local server. The local server sends it to the root server. All right, now the difference here is that rather than the root server simply replying with the TLD, in this case the root server talks to the TLD instead, asks them who is the authoritative server for the address in question. And then instead of, again, the TLD responding with that and then having the local ask, the TLD will respond again on your behalf. It will talk to the authoritative server, get the response, and then it'll just travel all the way back. So the same number of steps. Sometimes all or part of a DNS session is recursive. The difference here is that the servers are doing the requests on your behalf instead of the local DNS sending all the requests. So it reduces the amount of requests that the local DNS server has to do, but you'll note the total number of requests is still the same, and generally this is considered a bit more work for the root, the TLD, and the authoritative server to an extent. So in practice, we need a lot of caching to happen to make DNS performant, because having 4 round-trip times is a lot of latency and not a good experience for web browsers. So in practice, first, your computer saves resolved DNS requests. That might be the reason why I still can't access jager.crabdance.com, because it is saving the fact that this comes back as Nick's domain, and I have to dump my DNS records in order for it to try it again. Then your local server obviously doesn't talk to the root every time it wants to find a web page. In fact, the local server talks to the root very, very rarely. The registration for TLDs doesn't change very often at all, and since there's only 13 root servers in the whole world, they're pretty busy. So, I mean, they have multiple physical locations, but still, the world's a big place. They're very busy. So local servers will typically save the addresses, at least of the TLDs for the big ones, com, net, org, edu, all of those will be saved and updated pretty infrequently. Those caches last for hours, even days. So bringing us back around to cybersecurity, getting any of those servers along the way to store bad DNS resolutions, so to point to a place that is incorrect, is a very nasty attack indeed, and that's called DNS poisoning. So if you're trying to access catforums.com and it's at IP 1.1.1.1, and you're a nefarious attacker and you want to trick the user into visiting your bad website at 2.2.2.2, common attack is to try to get it so that that DNS request for catforums.com translates to your website instead, and the user ends up accidentally visiting your website instead. So this is the root of many bad attacks. If the root servers of the world were ever compromised, you could redirect the traffic of millions of users to other places where they weren't supposed to be going. You could redirect traffic to any .com, for example. You could say that all .coms go to the attacker's TLD, not the real one, and then they would redirect you to their own authoritative servers, not the real one, and then to their own websites, not the real one. So the root servers are a pretty big vulnerability on the internet, but as far as I know, they've never been meaningfully compromised, which is pretty neat. Likewise, the TLDs are a pretty big deal. If you could compromise the TLD for .com, that'd be pretty nasty. Authoritative servers do get compromised. I wouldn't say often, but occasionally. And that does tend to obviously cause a problem, as well as local servers can occasionally be compromised. And certain malware will just change your DNS settings to use the hacker's local service. That's also a simple trick you can use. So DNS is basically one of the weakest points of the global internet. Destroying or hijacking a portion of the DNS root servers can cripple the whole internet. And when a DNS root server goes down, it typically slows everybody down for quite some time. Prolonged outages there can be really crippling for the internet. Likewise, if big TLDs go down. There are many physical instances of the root servers, but again, most of them are concentrated in the US and North America. So anything that affects North America, like large-scale blackouts in this country, cripples the internet for the entire world, basically. Destroying or hijacking a TLD can cut out access to huge portions of the internet, com being the most obvious, but there are plenty of .net and .org websites that probably wouldn't be happy if their TLD got crippled too. Let's look at where they're at. So this is where all of the DNS servers are in the world. We're not going to pay too much attention to all the letters and whatnot. These are basically just copies of the 13 root servers and where they're at. So we see America has most of them, a lot on the East Coast, a lot on the West Coast, not a lot in the middle. So all you poor people in Colorado, you have to wait for your DNS requests quite a bit, 10 to 15 milliseconds just for the speed of light to make it to the East Coast. But not too long. Central America gets 1. Ouch. Now this is from 2006, so there have probably been quite a few more added. Central America had a lot less internet in 2006 than it does today. You'll also notice Canada doesn't have an awful lot, but most Canadians live next to the US border, so the places where there are root servers are where most Canadians live anyway, but they do tend to use US ones. South America also doesn't have a lot. Africa has barely any. Australia has 2. Almost nothing for the island nations. Japan's got a few, but China has barely any, considering how large China is. So a lot of this has probably changed in terms of there being more root servers in those countries now as they've gotten more internet adoption in the past 14 years. But the general picture remains the same, that most of the DNS roots are concentrated in North America and Europe. And the ones that are in Asia are concentrated in basically Japan and a small part of China. So that's it for DNS. If there are no questions, I'm going to move on to FTP for a bit. I still can't get to my website. Darn. It can take about an hour to update, and then again I might have to flush my DNS cache, which I don't want to do while I'm streaming because I don't know what impact that might have. I don't know what streaming relies on here. But if you are able to access your domain from your PC, let me know. Let's see. Able to access your domain by DNS instead of IP. See if anyone was able to do it. I assume that since you all made your requests after me, they processed after me. Oh, some of you got yours first? You jerks. Worked instantly for you. Grr. Give me mine. You were able to access mine. Okay, then I just need to flush my DNS cache. So this is an unfortunate part of DNS caching, is that if you get a bad response, your browser or your operating system or your router, any of those along the way can decide basically, oh, there was no response here, I don't have to check again. Or this was the IP that it's supposed to be at, I don't have to check again. And take a while for it to time out, so you might have to flush various things along the way before you actually get a response. So with that set up, we can actually go to the next step. If any of you want to do this, I don't think we will. We might give it a try on Friday, but it's a little bit tedious, and that is heading over to Let's Encrypt, or a different service, but Let's Encrypt is free, so it's the one we're going to use, and getting yourself a certificate in order to be able to run HTTPS, so that we can encrypt our traffic so that it doesn't show up in the clear, in the Wireshark text here. Of course, we don't want to see something like password in our HTTP traffic so that anybody can see it along the way. We want this to be encrypted traffic, so we would set up HTTPS, and the first step to doing that is to get a certificate, and then maybe we can see how we need to modify our Java code to accommodate HTTPS instead of HTTP in the fetch and push and so forth requests. Okay, well, with a minute left, I don't want to start a new topic, so I think I'm going to call it a day with that. Yeah, if you didn't already, get your DNS set up on free DNS. It doesn't last forever, but the free tier does last forever. You might have to refresh it at some point in your subdomains list. Now, a lot of the better DNS providers, or the paid ones, will also come with an application that you download on the server that you're running that will automatically update it for you whenever it changes, if you're not paying extra for the static IP. Although the vast majority of web services are hosted on static IP addresses, because if you're already going to be hosting a web service and developing it and paying money for hosting it and everything, you might as well pay the extra $10 a month or whatever for the static IP address. Okay, that's it for today. See you Friday for our last class, guys. And don't forget the homework due on Friday. I'm going to give you guys the take-home final on that day as well. Any questions? Let me know in Discord. See you then.